Hey guys, it's ADW, and today we are back in our Redstone computer, and it's been a while, and guess what? This time we are actually continuing our programming functions series. And it's funny because when I first made that first video where I was like, I don't know when I'm going to finish debugging this, I honestly had absolutely no clue. And little did I know that I was going to finish before I made the first video where I actually needed to use the computer. So, yes, this is actually where I was supposed to start using the computer stuff, and this point where I was supposed to skip over originally and just keep doing PowerPoints until I finished debugging. But as you guys can see, I have finished debugging, and it is a glorious day. I am so glad for this happening. Anyway, so let's talk about installing this guy. So, in the description of this video, not of the video that I made where I showed off everything, but in the description of this video there should be two links to two download files. And these files, one of them should be named Redstone Computer. That's the actual base Redstone computer. And the second one should be called Fibonacci. And that is a test program where we're basically just going to be calculating all the Fibonacci numbers within a certain range. And so basically the reason that we have this is that once we come in here, what we're going to do is, just to make sure that your computer is working just fine, we're going to go ahead and we're just going to turn the computer on and we're going to let it run. Now, it should take about 10 minutes for you to actually, for this program to do its thing. And you can wait in the AFK pool, but what I recommend doing is not only do you go in the AFK pool, but just do something else, because 10 minutes is a while, and not much interesting is going to be happening on the screen. Like you can see right now, nothing really is happening on the screen, so probably a good idea to just make yourself a snack and then just come back to this later or maybe do some homework or something like that. But anyway, I'm going to go ahead and cut till when this finishes, so yeah, I'll see you guys then. Alright, so it's been about 10 minutes, and now, as you guys can see, there are two things that should tell us that the program is done and everything has been done correctly. So the first one that you should be able to see is the one that's really right in front of us, the thing on the output panel. We can see the number 144 in binary, which is a Fibonacci number. I'm not sure which one it is. I think it's like the 8th or 9th, but that's irrelevant. All that matters is that it's the correct Fibonacci number that it should be outputting at this point. At least this program will, the last number that it should output is 144. Now the next clue that we can get that it's done is that we have got a little flashy light over here that is labeled program done. So that's just going to tell us that the program is done. So now let's talk about just a little bit about using the I/O here. So what we're going to do now is we're going to go ahead and flip the on-off lever. That's going to get rid of that light. And the other thing that turning this computer off will do that I never actually showed myself building, well, a lot of the stuff in the I/O that's not the main input panels I didn't actually show off, like everything that's not on this wall. So we've got actually I'm not sure if I showed I think I probably showed the stop command, but this button right here, which resets all the memory, this one is going to automatically reset the memory when we press it, and turning the computer off is going to reset the registers. So that's probably an important thing to know. But before we reset the memory, one thing that we can actually do is that if we come in here, we can actually see the actual memory, and we can see all of the Fibonacci numbers. So if you did not get 144 as your last output, you probably want to check through here and figure out what was going on. If nothing happened at all, then you should probably, there was probably a glitch with registers or something, And what you should probably do is you should try turning the computer off, making sure that all the registers are clear, and then try to restart the computer again. But anyways, if everything's fine like that, then we can move on to the next thing, which is where we're going to talk about how we're going to program this thing. So we're going to go into the actual world that doesn't have this program loaded in it, but is actually blank, so that we can start doing some basic instructions to show stuff off. Alright, so before we actually go into the computer and start sending instructions into our CPU, there's one thing that we want to do to make sure that stuff doesn't get out of control. That is that we're going to want to turn debug mode on. Now, what debug mode basically does is it makes it so that normally we have this clock up here, which is basically just this thing here. And this clock is basically going to go through, and every time, remember last time we were talking about how we have a data loop? Every time that we have information that is read from registers and saved somewhere, not necessarily registers, but anytime we have a data loop like that, it's going to take up one instruction. And this clock up here is basically just going through and just saying, okay, you finished this instruction, move on to the next one. So if we turn debug mode on, it's going to make it so that it's only going to do these instructions when we want it to. And this is really good because we don't want to have to just write a huge complicated program when we don't exactly understand how on earth this thing is even working yet. So that's why I've decided that it's probably going to be in our best interest for us to turn on debug mode. Now once we have debug mode turned on, we can simply turn the computer on, and you'll see that it is not going to actually turn the clock on. So with that out of the way, we can go ahead and we can start talking about the parts of the instructions in this computer. Alright, we are back, and now we are here in the ROM, and the ROM is basically the place where most of the instructions are going to be stored. By the way, I'm no clipping now. It's really convenient if you're actually programming this stuff to have single player commands and or no clip, because it's just going to make it a lot easier because it's pretty cramped in here. You can go through here if you don't have either, but it's just very inconvenient and it's much easier to flow freely. But anyways, so let's move on to what we talked about last time in terms of types of instructions. So you'll remember that last time we talked about having a data loop, and this data loop basically said we're going to have some information, it's going to be read out, it's going to be manipulated, and then it's going to be stored back somewhere else. And you'll remember that I said that each instruction in a computer is going to represent one individual data loop. So that's one process of information being read out, manipulated, and saved. So in order to get this, okay, 3, 2, 1. So in this computer, the way that we represent this entire instruction is in this particular bit layout, it's called. So over here, we have our first part, which is our source register and the register that we're saving to. So this guy right here is basically one of our most important things because it's just where we're going to be saving our information in the end. It's also going to read out, so if we were to do 1 plus 1 and one of our 1s was stored in whatever register we put in here. Remember, we have 4 registers. We have, and they can each be represented by placing, by the way that we make these into numbers is we're actually going to place torches on these wool blocks. Oh, and here's a good place to bring up the fact that if you accidentally break one of these things, don't worry, so long as you replace everything in the same way that it was originally laid out, everything should be just fine. But anyways, so if we wanted to use register, if we were to come back over here and we wanted to use register 0, then we would just put this. If we wanted to use register 1, we would put that, register 2, and register 3. And there, that's everything that we can do with these, depending on how we want to save them. This right here is a mode. We're going to talk about that later because that's pretty important. But for the moment, let's move on to the next big thing, which is our second register. Now this is the register that we're not saving, but if we were to be like adding or subtracting two numbers, this register would be really important if you think about it, because this register is going to be their second number. You can't add two numbers when you only have one. There's actually something special we're going to be doing this that we're going to talk about later, but for the moment we're going to move on to this part. And this part is the opcode. And the opcode is basically the part of the instruction that tells the computer what exactly you're going to be doing with this data. So we've read our data out of whatever this is, and we've read our data out of whatever this is. And this in here is going to tell us what we're going to do with it. Before things, but we're going to start talking about those now. Alright, so now let's talk about something that happens when, well, we only want to use one register for an instruction. Because not all of the time are we going to want to, say, add two numbers where we want to use two pieces of information. Sometimes we're only going to want to use one. And for these, this computer has an instruction format called a single operanded instruction. And it might seem silly to only use one register at a time, but there are all sorts of different instructions that we can actually do that only require us to have one operand. For example, bit shifting. This is something that's extremely valuable in multiplication and division. And we don't exactly need two registers to bit shift. We just need one that we want to shift over so many bits. Another common one is incrementing something. We don't need to use two registers to do that. We can just have one instruction that just says add 1 to this number. And we don't need to say, oh, we need to get a 1 into this register and then we need to add it into this one. No, that's really, really, really slow. It takes up register space, and it's just not a good idea in general. So, because of this, we have a single operanded instruction format where we only use one instruction. So, the way that we're going to do this is in our opcode, we're going to put in the code 11, which is the opcode for single operanded instruction. But wait a minute, there's all sorts of different single operanded instructions that we could do. We could increment, we could left shift, we could branch. So how do we define what that is? Well, because we're only using one register, we're just going to go over to this other register which we're not using because we only need one register for the information of the instruction. So what we're going to do is we're going to just put in whatever instruction we need into the information for register 2, which is these 3 bits. So if you do a bit of math, that makes it so that instead of having the 4 instructions that we would have if we just had these 2 bits in the middle determine all of the different instructions we could have, it's going to also allow us to do a total of 11 different instructions. So that is just about everything for that. But let's talk about this extra bit, which we've kind of been ignoring for a bit now. And this extra bit is called a mode. Now, what a mode is it's a really simple but powerful tool that we can use to expand the number of spaces that we have in our registers. So what a mode does is, well, whenever we're using a register, we can either have this mode bit be off or on. And if it's on, then what we're going to do is we're not going to use the information that's in the register as our operand. For example, if I wanted to add mode of register B plus mode of register A, we wouldn't add the value that's actually in these registers. What we would instead do is we would take the value in that register and we would use it as a pointer into memory. And we would use it like an address. So, up here in the main memory, which is, this is the main memory, which is RAM 32 bytes. Not much compared to what you might normally have today, but it's not bad for a Redstone computer. But anyways, So what we're going to do is we're going to take the value that we actually send that's actually stored in that register, and every single one of these addresses, it could be called by a single value in that register. So if I had the value of 0, then it would be this memory slot right here. If I had the value of 1 in that register that I'm using as a pointer, it would be this one. And this is really valuable. We're not actually going to be going into how useful it is today, but next time we're going to be talking so much about how useful it is to use a mode. So that's about it. So now we're going to move on to the next thing, which is branching. Alright, so now we're going to be moving on to the very last thing of today's video, and it's one of the most important ones and also probably the most complicated thing we're going to go over today, so bear with me, this might be a little hard, but overall it's not too hard compared to some of the stuff we're eventually going to get into, but all the same, it's kind of a jump from what we've been doing so far. And this is the topic of branching. Now, before we talk about branching, we have to kind of get a bit of context. So far we've been talking about individual instructions, an individual data loop, one loop where information gets read out of registers and saved back into some memory. It doesn't necessarily have to be registers, but I just used that as an example. Now, the thing is that we are generally going to, and this is actually down here in this computer, we're going to have this huge, vast array. Every single time you see something with black, red, and basically just not green, that's a different instruction that we can do. And it's a different place that we can input an instruction. But the thing is that normally we're just going to start off by doing this instruction, and then we're going to do this instruction, and we're going to keep going down there. But we don't always want to do that. And branching is a process that's going to allow us to not do that. Before we talk about branching, we're going to have to talk about a little something called flags, which actually has to do with the hardware of the computer. Now, a flag is basically a Boolean statement, and a Boolean statement is a true or false statement. So like, I ate lunch today, true or false, something like that. And it tells us something about what happened during the last data loop. So, for example, in this computer, or in computers in general, we have a limited number of digits. If I was to try to write out some number onto paper, and by the way, this is just an example, this doesn't have much to do with what we're talking about, but this is just going to allow me to explain one of these things. So if I was to keep writing something out on a sheet of paper, just like an infinite number of zeros, then I could represent a lot of data. But the problem is that in this computer, every single one of these, every single section of two different, just these two wires. We have 8 different combinations of these wires, and we can only represent numbers using these different binary numbers, or different binary wires, I should say. But because of this, it makes it so that 8 binary digits is only 255 different numbers, or 256 technically, but that's just the total number of numbers that we can actually represent with these 8 bits. And the problem is that what happens if we add 2 numbers together and it creates a number that's bigger than 255? All of a sudden we have a major problem. And what we do is we just cut that 8th bit off. But what we do with that extra wire is we're going to make that into one of our flags. So in the next instruction we could say, okay, we just added these 2 numbers together. Did it make a number that's too big for us to handle? And if it did, something's terribly wrong and we need to do something about it. So that's an example of something that you might do. Now usually you're just going to actually ignore that, and there's a lot of other stuff that you can do with that, but that is the basic idea behind it. And I kind of talked about how this ties into branching there, and that is that our actual branch instructions, which is the actual instruction that we need to call in order to do them, first of all, they're a single operanded instruction, so we're going to put 2 torches there. And then there's actually 3 different branching commands in this computer, and each of them uses a different flag. So, for example, if I wanted to do the one where if it's a carry out, or it's not just a carry out, also if there's shift overflow, we're going to talk about that in a bit, then I would do this. And then we're going to do something else with those bits down there. And then, if I wanted to do shift underflow, then I would do that. And that is the instruction for branch unconditionally. Now, let's talk about shift overflow and shift underflow. Now, one of the instruction types that I haven't talked about, which is one of our single operanded instructions, is something called a bit shift. And a bit shift is basically when we're going to take one bit, like this one, and we're going to just move it over to the next bit over, so like this one. So effectively, that's very useful because it allows us to multiply and divide numbers by whatever base we are. It's like, oh, here's a good example. In the actual decimal system that we're all used to, it's like just adding on a 0 to multiply something by 10. So one of our functions is just shifting left like that. And the reason that we can get another instance where we're going to create a number that's too big for the numbers that this computer can represent if we bit shift one of the really high significant digits. Because again, we have a limited number of digits that we can represent with the computer. So if we actually get into a scenario where we're having to shift something that's too big like that, and it shift overflows, then we're going to do that. And also, if we have like something here and we shift it off to the underflow, then it's going to be our shift underflow flag. The carry out and shift overflow flags are actually combined into one branching instruction. That's just because this computer has serious issues when it comes to space for, or at least different instructions that it can do, because it only has so many instructions that it can do with these 3 bits, or single operanded instructions. Alright, so we've got our flag and we've got the branching instruction filled out. Now there's just a few more things that we're going to want to do with these bits. Now the thing is that one of the things we're probably going to want to have if we want to go to a different instruction is we want to have the instruction number that we're going to want to go to. Well, that's simple enough. All we need to do is we just have a register that has that information stored in it, and then we're just going to call it using the same thing we would use for a normal register. Now, we can't actually use where that register is pointing. We have to use the value that is actually in that register, which is kind of unfortunate, but it does leave this bit open for us to do something with, because otherwise we wouldn't be able to do anything with this register. Sorry, otherwise we wouldn't have anything to do with this bit. Now, the thing that this bit does is in this computer, we have all these flags, right? But what if I want to do my branching command not if I had a branch carryout? So what if I want to branch not if I had a carryout, but if I didn't have a carryout? So like if I didn't have a carryout, so it's like a normal instruction, then I'm going to skip over all of this code that I would normally have to do that's going to be like really complicated to be like, oh, I had a carryout, oh dear, I have to go back and undo this or something like that. So what I could do is I could just use this thing, and if I turn this on, it's going to take the opposite of whatever flag is there. So if I did get a carryout, then it's going to treat it like I didn't. And if I didn't, then it's going to treat it like it did. So that's all that there really is for branching, and honestly all that we're going to be talking about today. Now, next time we're going to be going back to PowerPoints, and we're going to be talking about how we can use all the instructions we talked about today in order to make some of the really primitive, some of the really primitive high-level programming functionalities, and I can clearly talk today. But yeah, So that's it. I hope you guys have enjoyed, and I'll see you guys next time.